In the beginning, there was silence. Not silence as humans know it, but the silence before sound itself. A cosmos unlit, unformed, waiting for the first breath of creation. Then, in a fraction of a second, a great fire ignited. The newborn universe blazed with unimaginable heat, so dense and radiant that no particle, no photon, could break free. Light itself was imprisoned, woven tightly into a storm of matter and energy. For hundreds of thousands of years, the cosmos remained a furnace of blinding opacity. But as it expanded, it cooled. At last, a threshold was crossed. Electrons found protons, forming atoms. The fog lifted, and in that instant, light was released free for the first time to travel through space. That light has never stopped. Moving, it has crossed oceans of darkness, stretched thin by the swelling of the universe, until its fire dimmed to a whisper. Once brilliant beyond measure, it now glows only 3 degrees above absolute zero. And yet, it endures, spread across every corner of the sky. Astronomers call it the cosmic microwave background, but it is more than a faint radio hum. It is the first memory of the universe, the oldest light, carrying the fingerprint of creation itself. Encoded within it are patterns, ripples, and scars that speak of the universe's birth, its hidden ingredients, and perhaps even its fate. This ancient glow is not just a relic. It is a message written into the night, waiting to be understood. The question remains, what truths are hidden in the oldest light, still traveling through endless night? Chapter 1: The Noise That Changed Everything. The year was 1964. High above the marshlands of New Jersey, a massive, white horn-shaped antenna stood against the sky. It was a relic of the early space age, built by Bell Telephone Laboratories to listen for faint signals bouncing between Earth and the heavens. To most, it was an oversized piece of communications hardware. To Arno Penzias and Robert Wilson, to young radio astronomers, it became the stage for one of the greatest turning points in the history of science. Their task was straightforward: to measure faint radio waves with unmatched precision. Yet their work was interrupted by something stubborn, something that refused to vanish. Every time they turned their antenna skyward, a persistent noise filled their instruments, a steady hiss, like static on an untuned radio dot. At first glance, it seemed trivial. Engineers know the universe of radio signals is a messy one. Interference from the sun, the hiss of the atmosphere, even sparks from distant thunderstorms. But this was different. No matter where they pointed the horn, north, south, east, or west, the hiss remained. It was omnipresent. They began to suspect their equipment. Perhaps the amplifiers were flawed. Perhaps something was misaligned. Hours stretched into days as they recalibrated the machinery, testing every wire, every joint. The noise endured, and then came the pigeons. A pair had nested inside the horn, leaving behind feathers and droppings that scattered across the smooth metal interior. Penzias and Wilson suspected this organic intrusion might be the culprit, creating radio reflections, contaminating the signal. They climbed inside, cleaned it thoroughly, even captured the birds and released them far from the site. For a moment, the antenna stood pristine. But when the instruments were powered on again, the noise was still there. It had a temperature about 3.5 kelvins, just a few degrees above absolute zero. In radio astronomy, Noise can be measured as though it were heat, the gentle vibration of unseen particles. And this heat, though weak, was unshakable. It came not from a machine, not from the earth, not from the sun. It came from everywhere. What Penzias and Wilson could not know was that, only 60 kilometers away, a different group of scientists had been searching for exactly this signal. At Princeton University, Robert Dicke, Jim Peoples, and their colleagues had been theorizing about the afterglow of creation itself. They reasoned that if the universe began in a hot, dense fireball, as the Big Bang theory suggested, then its light should not have vanished. It should have stretched, cooled, and filled the cosmos as a uniform sea of microwave radiation. They were preparing to build an instrument to find it. But before they could, the Bell Lab's horn antenna had already captured it by accident. When Penzias and Wilson, puzzled and frustrated, reached out to colleagues for help, word spread quickly. A conversation linked the two groups. Penzias and Wilson had stumbled upon what Dicke's team had been searching for all along. The noise was not noise at all. It was the oldest light in the universe, the cosmic microwave background, the first observable fingerprint of creation. It was uniform across the sky, whispering the same faint message from every direction. This was no local interference. This was the cosmos itself, still echoing its birth cry billions of years later. In one instant, what seemed like a nuisance became a revelation. The static in their antenna became the most important discovery in cosmology. Since Galileo turned his telescope to the heavens, the universe had spoken, not with brilliance, but with a hum, not with spectacle, but with silence. The discovery reshaped everything. No longer was the Big Bang theory a speculative idea, competing with other models, such as the steady state. Now there was evidence, tangible and undeniable. The sky was glowing with the residue of the beginning, a fossil light that had traveled for 13.8 billion years to reach the instruments of two unsuspecting men in New Jersey. Penzias and Wilson did not set out to hear the universe's first song. They were looking for clarity in their instruments, not answers to the origin of time. But as often in science, the greatest discoveries appear as interruptions, whispers in the noise, accidents that cannot be ignored. This was not just a hum, it was the birth cry of space and time, stretched thin across eternity. And so, the antenna at Bell Labs became a telescope to the past, a doorway not to nearby stars, but to the very moment when matter and energy first separated, when the cosmos cooled enough for light to travel freely. The static that haunted their work became the most eloquent silence ever recorded, the echo of the beginning. Chapter 2: The Baby Picture of the Cosmos. For centuries, humanity gazed into the night sky with a silent question. Had the universe always been here, infinite and eternal? Or did it have a beginning? By the middle of the 20th century, two answers stood in stark opposition. One was elegant and comforting: the steady-state theory, proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. It described a cosmos with no birth, no death, a universe that forever stretched into the past and would forever extend into the future. As galaxies drifted apart, new matter would quietly appear, filling the gaps, maintaining cosmic balance. It was a universe immune to age, immune to time. The other vision was radical, unsettling, and far more dramatic. It suggested that the universe had not always existed, but had begun in a sudden act of creation. In a primordial fireball, space itself had erupted into being, filled with blinding light and furious heat. Over billions of years, that energy had expanded, cooled, and condensed into stars, galaxies, and planets. Georges Lemaître, a Belgian priest and physicist, first proposed this explosive birth in the late 1920s. But the term that stuck came later, coined half in mockery by Fred Hoyle himself during a BBC broadcast in 1949. He called it the Big Bang. For decades, these two competing visions divided cosmology. Observations offered hints, but no definitive verdict. Edwin Hubble had shown in 1929 that galaxies were rushing away from each other, suggesting an expanding universe. Yet expansion alone did not settle the argument. Was the cosmos expanding forever from a fiery beginning, or was it eternally stretching with no origin? And then came the noise. The faint microwave hiss captured by Penzias and Wilson's antenna was no ordinary interference. It was the light of creation itself, stretched and cooled by the passage of time. This light, the cosmic microwave background, or CMB, was older than galaxies, older than stars, older even than atoms as they are known today. It originated 380,000 years after the Big Bang, when the universe was still in its infancy. At that moment, the primordial fire had cooled just enough for matter and light to separate. Before then, photons had been trapped, endlessly scattered, by a fog of charged particles. But as the universe expanded and cooled, hydrogen atoms formed for the first time. The fog lifted, light was free, and it has been traveling ever since, stretched across the widening fabric of space-time. This fossil light carried a message. The universe was not eternal and unchanging. It had a beginning, a history, a childhood. For scientists, the implications were staggering. The steady-state theory, once considered elegant, once defended with passion, crumbled beneath the weight of this discovery. There was no way to reconcile a timeless, ageless cosmos with the uniform microwave glow that bathed the sky. The light was proof, undeniable and unyielding, that the universe had once been far hotter and denser than it is today. It was as if the cosmos had finally delivered its own birth certificate. The reaction in the scientific community was immediate and profound. For years, debates had been fueled by philosophy as much as physics. The steady state offered comfort, a universe without a beginning or an end. It spared humanity from confronting questions of ultimate origin, questions that drift uncomfortably close to philosophy and metaphysics. But now, the debate was settled. The cosmos did have a beginning. There was no avoiding it. Spoke of the discovery with A.W. Robert Dick himself. Upon hearing the news from Penzias and Wilson, is said to have turned to his colleagues and remarked, "Well, boys, we've been scooped." The signal they had been preparing to find had already been captured, but more than that, the noise confirmed a vision of the universe that many had suspected, but few had dared to believe was provable. The cosmic microwave background was not just evidence, it was a window into the past, a photograph, faint, blurry, but astonishing, of the infant universe. For the first time in human history, it was possible to look back beyond the stars, beyond the galaxies, into a time before structure, before form, before the universe was recognizable. This realization rippled far beyond physics. For philosophers, theologians, and ordinary people alike, the discovery carried an existential weight. The universe was not eternal and unchanging. It had a birthday. And if it had a birthday, what lay before it? What does it mean for something as vast as the cosmos to begin? The cosmic microwave background forced humanity to confront its own impermanence. If the universe had a beginning, might it also have an end? For cosmologists, however, the CMB offered something even more practical, a treasure trove of information. This faint afterglow encoded the conditions of the early universe. Its temperature, its density, its composition, all were written in the patterns of that ancient light dot. To the naked eye, the microwave background appears almost perfectly uniform, the same in every direction. But with sensitive instruments, tiny fluctuations are revealed, minute ripples, variations in temperature no larger than 1 part in 100,000. These ripples were the seeds of everything. They marked the places where matter was ever so slightly denser, destined to collapse under gravity, to form the first stars, the first galaxies, the vast cosmic web that still stretches across the universe today. From these faint variations, the grand structures of existence were born. In this sense, the CMB is not only a baby picture of the cosmos, but a map of its future. The discovery also marked the beginning of precision cosmology. For the first time, scientists could move beyond speculation and build a quantitative history of the universe. They could measure its age, its rate of expansion, its composition. The CMB became a ruler, a clock, and a code, all at once. And yet, beyond the equations and measurements, the discovery carried a deeper resonance. Humanity had reached across 13.8 billion years of time and touched the moment when the cosmos first became transparent to light. The photons that streamed into Penzias and Wilson's antenna had been traveling since long before Earth existed, long before the sun ignited, long before even the Milky Way had taken shape. Each photon was a messenger from a time when the universe was only a few 100,000 years old. To grasp them was to hold in one's hand a fragment of the beginning. This was more than science. It was revelation. The philosophers of the steady state had spoken of a universe without origin, a cosmos immune to birth and death. Now the evidence in the sky spoke otherwise. The universe was young once. It grew, it changed, it carried history within it. And if it began, then perhaps it is not eternal after all. For many, this realization was unsettling. For others, it was exhilarating. It meant that the greatest questions, once thought to belong to poets and theologians, could now be addressed with data, with instruments, with physics. The question of beginnings was no longer beyond science. The cosmic microwave background became a symbol, humanity's first direct glimpse of the origin story written into the fabric of reality. It was not a story carved in myth, nor inscribed in scripture. It was a story carried in light itself, etched across the sky in a silent glow. What had seemed like noise was, in truth, a whisper from the dawn of time. And with it, the universe had revealed its most intimate secret, that it was born, that it had a childhood, that it carries its memory forever in the faintest glow of night. This was not only the death of the steady-state model, it was the birth of modern cosmology. In the silence of a horn-shaped antenna, humanity found the echo of creation. And in that echo, the universe was no longer eternal, no longer immutable. It was alive with history. It was a cosmos with a past, a cosmos with a beginning, a cosmos that had spoken. And in that revelation, humanity was left not with answers, but with deeper questions. If the universe had a beginning, what came before? If the universe has a childhood, what is its destiny? And if the cosmos itself carries memory, what does that mean for the fragile consciousness within it? A consciousness capable of hearing that faint and ancient hum. The cosmic microwave background was more than light. It was a mirror, and in its reflection, humanity caught its first glimpse of eternity. Chapter 3 Ripples in the Oldest Light. The faint glow that Arno Penzias and Robert Wilson uncovered in 1964 was a revelation. Yet at first, it was also a mystery wrapped in simplicity. The hum was uniform, the same across the entire sky. It was a discovery powerful enough to shift the foundation of cosmology, but incomplete, a first glimpse of something vast and unfinished. If the microwave background truly was the afterglow of a cosmic fireball, then it must carry more than uniformity. It must hold a pattern, a texture, a record of the first imprints of structure. For decades, theorists whispered of faint irregularities, tiny wrinkles in the ancient light that might explain why the universe is not smooth, but filled with galaxies, clusters, and voids. Without such variations, matter would never have clumped together. Stars would never have formed. The night sky itself would not exist. The task ahead was daunting: to measure the background with precision far beyond the crude instruments of the 1960s. Scientists turned to the skies themselves, not the endless heavens of astronomy, but the literal sky above Earth. In the 1970s, high-altitude balloons lifted sensitive radiometers above the bulk of the atmosphere. From these fragile platforms, drifting with the winds at the edge of space, came the first hints of refinement. The radiation was indeed close to the spectrum of a black body, the pure curve of heat radiation emitted by something that had once been unimaginably hot. But the measurements were crude, the data uncertain, blurred by noise. It would take something greater, not a balloon, but a satellite, to reveal the true message hidden in the glow. In 1989, NASA launched the Cosmic Background Explorer, or COBE, a modest spacecraft by the standards of planetary missions. COBE carried instruments of extraordinary sensitivity. Its purpose was simple in description, but monumental in consequence: to measure the precise spectrum and structure of the microwave background. When the data arrived, the results stunned the world. COBE revealed that the microwave glow matched with exquisite perfection the curve of a black body spectrum. Its temperature was measured at 2.7 to 6 kelvins, just 2.7 degrees above absolute zero. The fit between theory and observation was exact, more precise than any experiment in physics had ever achieved. It was the most perfect black body curve ever measured in nature. This was not a coincidence. It was a signature. Only a universe born in a furnace of unimaginable heat could produce such a spectrum. No star, no dust cloud, no galactic process could mimic it. This was direct proof of the primordial fireball. The Big Bang was no longer just a compelling idea. It was written into the very shape of the light across the heavens. Yet COBE did more than confirm the fireball. It also uncovered something far subtler, far more profound. In the faint glow, COBE detected tiny fluctuations, anisotropies, variations in temperature across the sky no larger than 1 part in 100,000 to the human eye. They were invisible, but to COBE's detectors, they were there, delicate ripples in the ancient light, patterns that had traveled across 13.8 billion years of space-time. These ripples were not random noise. They were the seeds of everything. They marked the places where the density of matter in the early universe was ever so slightly greater or smaller. Over billions of years, gravity would amplify these differences. The denser regions would draw in more matter, collapsing into the first stars, the first galaxies, the vast filaments of clusters and superclusters that define the cosmic web. The emptier regions would become the voids, vast expanses of near nothing, stretching across millions of light-years. In these tiny variations lay the blueprint of the cosmos. The architecture of existence was written into the first light, long before galaxies burned or planets formed. The scientific community was shaken once again. For decades, the CMB had been considered smooth, uniform, a cosmic wallpaper. Now it was a map filled with hidden detail. The Nobel Prize in Physics was awarded in 2006 to John Mather and George Smoot, the leaders of COBE's measurements. Smoot famously remarked that looking at the COBE maps was like looking at the face of God. It was not poetry alone. The images represented humanity's first view of the primordial fingerprint that shaped everything to come. Philosophically, the discovery carried a weight beyond physics. The fluctuations in the CMB suggested that the universe's vast structure was seated in the tiniest imperfections. Without those ripples, there would be no stars, no galaxies, no Earth, no life. The smoothness of the fireball needed to be ever so slightly broken, so that form could emerge from chaos. In those imperfections lay the possibility of everything. It is humbling to consider the great spirals of galaxies, the blazing birth of stars, even the existence of human thought, all trace back to fluctuations no larger than a few tens of microkelvins in an ocean of ancient light. The entire cosmos emerged from a fabric that was almost, but not quite, uniform. What causes such primordial ripples? Theorists turned to ideas of quantum mechanics and inflation. According to inflationary theory, in the first fraction of a second after the Big Bang, the universe expanded faster than light itself, stretching tiny quantum fluctuations to cosmic scales. These fluctuations became the seeds of structure, frozen into the fabric of spacetime. Billions of years later, they appeared in COBE's maps as faint modeling, tiny variations that would grow into galaxies and stars. Thus, in the ripples of the microwave background, scientists glimpsed not only the history of the universe, but its earliest physics. The CMB carried the fingerprints of processes that occurred in less than a trillionth of a second after creation. It was not just a baby picture, it was the ultrasound of cosmic birth. For humanity, COBE's revelations were transformative. A small satellite had reached across almost 14 billion years and shown us the first imperfections, the first hint of structure. The night sky was no longer a random scattering of galaxies, but the outgrowth of tiny, ancient fluctuations. The universe was not arbitrary. It was patterned, coded, structured from the very beginning. But perhaps the most profound realization was this: in the very earliest light, the seeds of life itself were already sown. Without ripples in the fireball, matter would have spread evenly across space, thin and unchanging. There would have been no stars to forge heavy elements, no planets to cradle oceans, no molecules to assemble into living cells. The smallness of the fluctuations, neither too large nor too small, made existence possible. The CMB was not only a map of the universe's infancy, it was a map of destiny. From Kobe forward, humanity entered a new era of cosmology. The discovery of anisotropies opened a gateway to precision measurements, to mapping the universe's geometry, composition, and fate. Later missions, WMAP, Planck, would sharpen the image, refining the measurements to exquisite accuracy. But it was COBE that first revealed the texture of the oldest light, a universe that began in fire, cooled to silence, now spoke in ripples across the microwave. The discovery redefined cosmology as both a science and a philosophy. For here was proof that the vastness of existence was born from subtlety, that the grandeur of galaxies arose from minute whispers in the background of time. The cosmic microwave background, once dismissed as static, was now understood as scripture, written in radiation, the oldest record we possess. And as scientists gazed upon the modeled maps returned by COBE, they realized they were staring at nothing less than the origin of structure, the beginning of form, the blueprint of everything that would ever exist. In those ripples lay the story of galaxies. In those ripples lay the story of stars. In those ripples lay the story of life. The universe had taken its first breath and left the imprint of that breath forever in the faint glow that surrounds us still. Chapter 4: The Puzzle Written in Fire. By the dawn of the new millennium, the cosmic microwave background was no longer a curiosity. It was the foundation of cosmology, the relic light that had transformed speculation into science. Kobe had shown the first hints of structure in that ancient glow, proving that the seeds of galaxies were present in the earliest times. Yet Kobe's vision was blurred, its resolution coarse. Then Kobe could reveal an intricate tapestry of fluctuations, delicate and precise, waiting to be uncovered. If these patterns could be mapped with clarity, they would unlock answers to questions of staggering scale, the exact age of the universe. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, better known as WMAP, from its vantage point 1,000,000 miles from Earth at a gravitational balance point known as L2. WMAP scanned the heavens with unmatched precision. For 9 years, it observed the microwave background, measuring variations as small as tens of millionths of a degree. The results were breathtaking. For the first time, the infant universe appeared before humanity, not as a blur, but as a portrait. The mottled sky, painted in faint blues and reds, revealed patterns of hot and cold fluctuations in the density of the early plasma, stretched across the entire cosmos. It was more than an image. It was a cosmic fingerprint, a snapshot of the universe when it was only 380,000 years old. From it, scientists derived astonishing truths. The universe was 13.7 billion years old. Only 5% of it was ordinary matter. About 25% was dark matter, and nearly 70% was something stranger still, dark energy, a force driving cosmic acceleration. WMAP did not just refine cosmology, it created what came to be called the Standard Model of Cosmology, the CDM model, a universe composed mostly of the unseen, born from a hot fireball shaped by gravity and destined to expand ever faster. But the background light was not finished with its surprises. In 2009, Europe's space agency launched an even more ambitious mission, the Planck satellite, with instruments cooled to near absolute zero. Planck measured the microwave background with unprecedented accuracy, resolving details finer than a tenth of a degree. For 4 years, it traced the entire sky, capturing the most detailed portrait of the early universe ever achieved. The results were both triumphant and troubling. On one hand, Planck confirmed the Big Bang model with dazzling precision. Its maps of the anisotropies matched theory almost perfectly, cementing our understanding of inflation, dark matter, and dark energy. Cosmology, once speculative, now rested on a solid observational foundation. But hidden within the perfection were anomalies, subtle irregularities that defied expectation. The most famous was the cold spot, a vast region of the southern hemisphere, of the sky hundreds of millions of light years across, where the CMB appeared significantly colder than the surrounding regions. Statistically, such a feature was improbable, not impossible, but unlikely enough to spark debate. Was it a random fluctuation, a cosmic coincidence, or was it something deeper, a scar left by events beyond the visible horizon? Other anomalies emerged as well. The background showed slight asymmetries between the northern and southern hemispheres. One half of the sky seemed to contain slightly stronger fluctuations than the other. Even stranger, some of the largest scale patterns in the CMB appeared to align along a single axis, nicknamed the axis of evil. It was an unsettling phrase, but it captured the unease. The cosmos seemed to display alignments that should not exist in a universe born from randomness. These anomalies resisted easy explanation. They were faint, subtle, hidden within the noise. Yet they lingered, refusing to vanish even as Planck sharpened the view. For cosmologists, they became both a fascination and a frustration. If real, they might hint at physics beyond the known universe. Some speculated they could be traces of cosmic defects, scars left over from phase transitions in the early universe, when fundamental forces separated and the laws of physics took their present form. Others imagined more radical possibilities, that the cold spot might be the imprint of a collision with another universe. Was speculative, but haunting. If true, the microwave background was not only a window into our universe's birth, but a clue to realities beyond it, realms forever hidden. Perhaps the anomalies were simply statistical flukes, the inevitable oddities that appear when measuring vast datasets. Perhaps they were illusions born from the way human minds search for patterns, eager to find meaning even in randomness. The debate continues. To this day, what is certain is that the CMB, once seen as proof of cosmology's triumph, has become its most tantalizing puzzle. It offers not only confirmation, but questions that reach to the edge of knowledge. Philosophically, the implications are profound. The cold spot and its kin remind humanity that even in the clearest maps, the universe resists total comprehension. The cosmos gives answers with one hand and deepens mystery with the other. It is a paradox written into light itself that remain forever beyond reach. In this way, the CMB is not just evidence. It is a mirror of human inquiry itself. Clarity entwined with doubt. Discovery intertwined with mystery. For in the oldest light of the universe, humanity sees both its triumph and its limits. The map of the cosmos is not the end of the story. It is the beginning of new enigmas, new horizons, new questions written in the glow of creation. The universe has revealed its face and hidden something just beyond the veil. Chapter 5 Whispers from the First Instant. The cosmic microwave background is not only an image of the young universe, it is a canvas painted with physics at the edge of imagination. Every ripple, every subtle variation in its glow, is a relic of forces that acted when the cosmos was younger than a heartbeat, when the laws of nature themselves were still forming. To study this light is to peer into moments so brief they defy comprehension. The first trillionth of a second, when space expanded faster than light, when the seeds of all structure were born. This idea is known as cosmic inflation, proposed in the 1980s by Alan Guth, Andre Lind, and others. Inflation suggests that in the tiniest sliver of time after the Big Bang, the universe swelled by a factor so immense it is almost unspeakable, perhaps 10 in volume, achieved in less than 10 seconds. A process so sudden, so violent, that it smoothed the cosmos to near perfection. Inflation explained mysteries that had long haunted cosmologists. Why is the universe so uniform across vast distances? Why does space appear flat, as if geometry itself were stretched taut? The answer, inflation suggests, is that all irregularities were ironed away by this surge of expansion. What remained were only the faintest imprints, quantum fluctuations magnified by inflation into the seeds of galaxies, and those imprints are visible today in the microwave background. The tiny anisotropies, mapped by Kobe, WMAP, and Planck, are precisely the kind of ripples inflation predicts. In their statistical patterns lies evidence that quantum processes shaped the largest scales of reality. Here, the smallest and the greatest are bound together. Quantum uncertainty, the flicker of fields at subatomic scales, became the architecture of the cosmos. Yet the microwave background reveals more than inflation's signature. Hidden in its ripples are the fingerprints of dark matter, the unseen. Mass that outweighs ordinary atoms 5 to 1. The CMB's fluctuations show how matter clumped in the early universe. Ordinary matter, made of protons and electrons, interacted with radiation, creating waves in the primordial plasma, acoustic oscillations, like sound rippling through a vast cosmic fluid. But dark matter, immune to light, behaved differently. It did not scatter. It pulled silently, gathering matter into gravitational wells that would one day grow into galaxies. The pattern of peaks and troughs in the CMB's temperature fluctuations bears witness to this invisible scaffolding. Without dark matter, the universe we see, the spirals of galaxies, the clusters bound across millions of light years, could never have formed. The microwave background carries its mark, silent but undeniable, and woven into this ancient light is a stranger influence. Still, dark energy. The CMB photons have traveled for nearly 14 billion years, crossing an evolving universe. As they journeyed, the growth of cosmic structure and the acceleration of expansion left subtle imprints on their paths. This effect, known as the integrated Sachs-Wolf effect, is faint but detectable. It reveals that the expansion of the universe is not slowing but speeding up in the background glow. The hand of dark energy is inscribed, a force that makes up nearly 70% of the cosmos, yet whose nature remains unknown. Thus, the CMB does more than tell us of the beginning. It speaks of the unseen majority of existence, dark matter and dark energy, the two forces that shape destiny. But the anomalies hint at something deeper still: the cold spot, the strange asymmetries, the alignments that seem to defy chance. Could these be scars of a wider reality? Some theorists suggest they may be the fingerprints of false vacuum decay. In the language of quantum fields, our universe may not rest in the most stable state. Instead, it may dwell in a false vacuum, a temporary plateau of energy. If so, then the cosmos we see is but one bubble among countless others, each forming when inflation ended in different regions of space. The cold spot in this picture could be the bruise left by a collision where our bubble universe brushed against another. If true, the microwave background is more than a baby picture of our cosmos. It is evidence of a multiverse. Such ideas are speculative, and many cosmologists caution restraint. Anomalies may vanish under new analysis, explained as chance. Yet the possibility lingers. The background light is the only messenger from the first instant, and within it, whispers may remain of events beyond our horizon. At the heart of these mysteries lie quantum fields. Modern physics describes reality not as particles alone, but as fields stretching through space. Every particle is a vibration of a field, every force a ripple in an invisible medium. In the first fractions of a second, these fields were in turmoil. Gravity, electromagnetism, the nuclear forces, all may have been unified, indistinguishable. As the universe cooled, they fractured, breaking symmetry, leaving behind the laws we know. The CMB carries the aftershocks of this transition. It is a fossil not only of matter and radiation, but of the birth of physics itself. Yet here, the questions darken. For the microwave background does not simply reveal answers, it points to the edges of comprehension. Inflation, dark matter, dark energy, the multiverse, all remain theories, supported by hints, yet incomplete. The CMB is both confirmation and enigma. It proves the Big Bang, it proves the fireball, it proves the growth of structure, but it also whispers of realms we cannot test, fields we cannot touch, worlds we may never see. Philosophically, it leaves humanity in a strange place. To look into the microwave background is to see both the clarity of science and the shadows beyond its reach. The cosmos has given us its baby picture, but the photograph is both detailed and unfinished, as if the universe has shown us its face while still concealing its soul. What is the nature of inflation? What is dark matter? What is dark energy? Are we a single bubble or one among countless universes? The microwave background does not answer. It only invites. In its faint ripples lie the physics of the first instant, the architecture of structure, the promise of questions still unformed. It is proof and it is puzzle. It is clarity, and it is mystery. And in that duality, perhaps, lies the deepest truth, that the universe is not meant to yield all at once, but to reveal itself slowly, light by light, whisper by whisper, across the gulf of time. The background glow is the oldest story ever told, but it is also the newest, for in its silence, new questions are born with every generation that listens. The cosmos has left us its memory. It is now for us to decide what to do with its mystery. Chapter 6. The silent glow under scrutiny. Across the heavens, the ancient light still lingers, a faint whisper of fire, stretched thin by the expansion of space, cooled to just a few degrees above absolute zero. It is everywhere, unblinking, a cosmic afterglow woven into every corner of the sky. Yet to human eyes it is invisible. Only the most sensitive instruments, shielded from Earth's interference and tuned 2-millimeter wavelengths, can reveal its hidden language. For half a century, scientists have pointed their telescopes toward this dim radiation, from the Kobe satellite to WMAP, from Planck to observatories in the high deserts and frozen poles of Earth. Each effort has sharpened humanity's vision of the early universe. The work is relentless, painstaking, for the clues are faint. But in this faintness lies truth, the first light of creation, encoded with secrets of time itself. The European Space Agency's Planck satellite, launched in 2009, remains one of the greatest triumphs in this pursuit. Orbiting far beyond the noise of Earth's atmosphere, Planck mapped the sky with exquisite precision, revealing the cosmic microwave background in unprecedented detail. Its data set the gold standard for cosmology, refining the age of the universe to 13.8 billion years, weighing the proportions of dark matter and dark energy, and uncovering anomalies that continue to provoke debate. Yet, even Planck's portrait is not the end. Across the globe, new telescopes rise to push further. In the arid air of Chile's Atacama Desert, nearly 5 kilometers above sea level, the Atacama Cosmology Telescope stares at the night sky. Its location is no accident. The thin atmosphere there offers one of the clearest windows on Earth for microwaves streaming from the cosmos. At the opposite extreme, on the Antarctic Plateau, the South Pole Telescope conducts similar studies, where the air is so cold and dry that it mimics the clarity of space itself. Together, these instruments continue the work begun by satellites. They are building sharper maps, refining polarization measurements, and probing the cosmic microwave background with sensitivity Planck could not reach. For polarization is the new frontier. The microwave background is not merely warm or cool, brighter or dimmer. It carries subtle orientations of light patterns etched by the scattering of photons in the primordial plasma. These patterns divide into 2 types, E modes, smooth and radial, already mapped with precision, and the rarer, more elusive B modes, twisting and curling like faint swirls across the sky. The detection of B-mode polarization is one of the most ambitious goals in all of cosmology. For hidden in those curls may lie the fingerprint of gravitational waves from inflation. If the universe truly expanded at unimaginable speed in its first instant, it would have shaken the very fabric of spacetime. These tremors, born from the quantum foam itself, would have imprinted a unique signature on the microwave background. Unlike ordinary density ripples, these signals would appear as a subtle curl in polarization. The long-sought B- modes to glimpse them would be to glimpse the hand of inflation directly, a window into physics at energies far beyond any particle accelerator on Earth. It would confirm that the cosmos began with a surge of expansion, and perhaps even illuminate the nature of the fields that drove it. Yet the signal is vanishingly faint. Dust in our galaxy emits polarized light as well, masking the cosmic pattern. The story of the BICE P2 experiment in 2014 illustrates this difficulty. Initial results seemed to reveal the inflationary signature, a discovery hailed as revolutionary. But later analysis showed that galactic dust had mimicked the pattern. The cosmos had withheld its truth once again. Still, the effort continues. Future missions, like Light by RD, a Japanese-led satellite scheduled for the 2030s, are designed specifically to search for these faint swirls. From orbit, shielded from terrestrial interference, Light by RD will scan the sky with sensitivity tuned to inflation's possible imprint. If it succeeds, humanity will have touched the first trillionth of a second with evidence written in light. But the cosmic microwave background speaks in more than polarization. It is also bent and distorted by the very matter it encounters on its billion-year journey. This effect is known as gravitational lensing. As CMB photons travel through the cosmos, the gravity of galaxies and dark matter halos deflects their paths. The effect is slight but measurable. By studying the distortions, scientists can map the invisible distribution of matter across the universe, even the dark matter that cannot be seen by any telescope. Thus, the background glow serves as a lantern, illuminating the otherwise hidden web of structure that threads through the cosmos. Each warped photon tells of an unseen gravitational hand, and by gathering them, scientists reconstruct a cosmic cartography, the scaffolding of galaxies, clusters, and superclusters traced across billions of light years. The microwave background also stands at the intersection of cosmology and particle physics, for in its precision lie hints of particles scarcely understood. The standard model of physics predicts the behavior of known particles, but the CMB is sensitive to even the faintest deviations, the way neutrinos, nearly massless, ghost-like, particles, streamed through the early plasma left subtle imprints on the background. Planck's data already constrain the number of neutrino species and hint at their collective mass. Future experiments may sharpen these limits, narrowing the window on the neutrino's hidden role in cosmic evolution. Beyond neutrinos, theorists suggest that exotic particles such as ixions, hypothetical relics from high-energy physics, could leave fingerprints in the CMB. These particles, if they exist, might solve the puzzle of dark matter or point toward new physics beyond the standard model. Their presence would subtly alter the way fluctuations evolved, leaving traces in the statistical patterns of the ancient light. Thus, every refinement in measurement is not only a triumph of astronomy, but a probe of fundamental physics. The CMB is a meeting place of the very large and the very small, cosmologies, vast scales converging with the subatomic world. Yet perhaps the most remarkable truth is how fragile all of this is. The signals that reveal inflation, lensing, neutrinos, or ixions are buried in a glow scarcely 3 degrees above absolute zero. The difference between discovery and silence lies in measurements of millionths of a degree, extracted from an ocean of noise. It is a pursuit that requires patience, precision, and faith in the power of faintness. For the microwave background is not loud. It does not blaze like a quasar or erupt like a supernova. It whispers, and humanity has built an entire science on listening to that whisper. Each telescope that stares into this glow is part of a larger human story. Across continents, through the silence of polar nights and the dryness of desert air, teams of scientists and engineers work to wring meaning from near nothingness. Decades of effort converge on a signal weaker than the hum of a refrigerator, older than any star, and still the work is not finished. Every new generation of instruments asks sharper questions. Is inflation real? And if so, how did it unfold? What is the mass of the neutrino? Does dark matter consist of ixions or something stranger still? Are the anomalies truly whispers of other universes or the mirages of randomness? The cosmic microwave background holds the key to each. It is the one relic that carries across the entire history of the cosmos. A messenger untouched by the ages, waiting to be read with greater clarity. Philosophically, there is something humbling in this pursuit. Humanity has built machines on mountaintops and in orbit, not to search for wealth or power, but to capture a light so weak it is almost silence. A light that speaks not of now, but of then, the first instant when all that exists was compressed into a fireball beyond comprehension. To listen to this light is to participate in an act of cosmic remembrance. It is to hear the universe telling its own story, one that predates planets, suns, and even the atoms of human flesh. The effort continues, not because the answers are certain, but because the questions are worthy. The background glow reminds us that even in near nothingness, meaning can be found. That even in a signal just above absolute zero, there can be warmth enough to illuminate creation. The cosmos has given its faint memory. Humanity, restless, continues to ask it for more. Chapter 7. The Oldest Traveler. It has been moving through the cosmos for almost 14 billion years. Older than stars, older than galaxies, older than the earth beneath human feet. It is the most ancient traveler of all. The cosmic microwave background has crossed the ages in silence. Its photons, untouched by time's decay, they have streamed across the vastness of space with perfect fidelity, carrying with them a record of the universe's first breath. This light began its journey when the cosmos itself was young, only 380,000 years old. In that epoch, the primordial fireball finally cooled enough for atoms to form. Electrons bound to protons, the fog of plasma lifted, and light was at last free to travel. Those photons have never stopped moving. They have not aged, though the universe around them has grown ancient. Every star that has burned, every world that has formed, every living being that has breathed, has done so while these photons continued their long voyage. They are older than memory, older than the concept of memory itself, and yet they are still here, surrounding the Earth, entering every telescope, tuned to their frequency, whispering their message to anyone who will listen. What does this light reveal? That the universe has a beginning, that time itself has an origin point, that everything visible today, from galaxies of 1 trillion stars to the fragile veins of a leaf, emerged from faint ripples in this first light. Those ripples were small, almost imperceptible, yet across billions of years, gravity amplified them. Hills of density became galaxies, valleys became voids. Structure arose from chaos. Order was written into the universe, not imposed from outside, but seeded from within, from the very noise of quantum fluctuations stretched across space by inflation. To look upon the microwave background is to look at the raw material of existence before form, before history. It is to witness the infancy of everything, and yet, even in its clarity, there are shadows. The cold spot, vast, improbable, perhaps a clue to a greater reality. The asymmetries, alignments across the sky that suggest a hidden order beyond randomness. The slight tensions in measurements, hints that something is missing from our equations, something unaccounted for in the story of creation. These anomalies remind humanity of a simple truth, even in the oldest light. Understanding is incomplete. The cosmos has revealed its outline, but the full picture remains veiled. What lies beyond the observable horizon? What physics governed the first instant? Are there other universes brushing against our own, their scars faintly marked in this ancient glow? The cosmic microwave background is more than a relic. It is a mirror. On one side, it reflects the beginning of everything, the hot, dense origin, the seeds of galaxies, the proof that the universe is not eternal but was born in fire. On the other side, it reflects humanity itself, its questions, its limits, its unending search for meaning. One face shows clarity, the other shows mystery. Philosophically, it is both comforting and humbling. Comforting because it proves that science can reach back to the dawn of time and touch its light. Humbling because it shows that even the clearest evidence carries questions it cannot answer. The photons still travel. They will cross the universe long after stars have burned out, long after Earth has been forgotten. They will move through the silent night for trillions of years, fading ever colder as space expands. And perhaps, if observers exist in some unimaginable future, they too will see this glow and wonder at its meaning. As long as the light endures, so too will the search. For to be human is to ask, and to ask is to look outward. The microwave background is not only the memory of the cosmos, it is a reminder that memory itself can inspire, that in chasing the faintest whisper of light, humanity is really chasing itself, its origin, its place, its purpose. The oldest light keeps traveling through endless night, and so the search continues.